In today's episode, a 3D printed bearing is rolling over the table, Matt is printing a box, and a secret guest joins him in his workshop. Hey and welcome back to my channel. I'm Matt, the printing nerd, and today is Q&A time. And as you know me, I'm a big fan of show, don't tell. So buckle up for some crazy fast 3D prints. My first question is about quality and about accuracy. Many people believe that when you print at speeds around 400 or 500 millimeters per second, the accuracy of the 3D printer decreases and the quality of the prints suffer. And in principle, I would agree with you. So let's have a look how accurate we are at highest speeds. I would like to start with a printed bearing. This print-in-place print has two challenges. First, bed adhesion. If you look at the model in Cura, we notice that we have to print 12 balls that stands on a tiny blob of filament. The slightest inaccuracy causes the balls to detach from the print bed and ruin the print. We also have two rings that, with tolerances of 0.2 millimeters, don't offer much room for error. Let's take a closer look. The layer lines look pretty good. The bearing rotates without resistance. The top surface looks also fine. I can't feel any resistance or scratching when turning the balls around, and as you can see, the balls move freely. A good start. But let's dig a bit further. My next print is a print-in-place tolerance test. I've printed it at speeds of 500 millimeters per second. This simulates a worst-case scenario, because normally you would print outer perimeters and top and bottom layers at way lower speeds. But I was curious to see how the printer behaves in such an extreme scenario. So let's see how many elements could be moved freely. This demonstration showed us that all elements up to 0.2 millimeters moved freely. The 0.2 mm element had some issues as there was initial binding. However, the 0.15 mm element runs smoothly without binding. Let's have a closer look. You can see those small dots. It appears to me that at those points the filament got stuck, requiring some wiggle to free it. Since those dots are sporadic, I think they are extrusion related. My guess would be that at those points pressure advanced caused an over-extrusion which glued the element to the housing. In contrast, the 0.15 element runs freely without sticking, which is also a sign to me that the motion system is able to handle that speeds pretty well. Regarding the 0.1 mm element, I can say that it wobbles and with a bit of force it could likely be released. This shows me that the printer's motion system is able to print at an accuracy between 0.1 mm and 0.15 mm, but is held back by the Bowden extruder. This is an issue that I noticed already in multiple situations in the past, and we will see in this video that it will become more and more the main topic of the next printer's iteration. The development of a direct drive extruder already started. I've printed my first prototype out of PLA and I was able to get really good promising results. My goal is to release it to my Patreons in the next couple of weeks. So if you want to be one of the first people out there testing this new direct drive extruder, consider becoming a Patreon. But this made me curious. I wanted to learn more about the extruder and how it behaves in an extreme scenario. I found this pie tower and I thought it would make a good torture test for the extruder. Once again I started a print at 500 mm per second speed, as you can easily see when I print the base plate. But as soon as the printer reaches the small parts of the tower, the printer suddenly slows down. The reason for this is that the features we print are pretty small. They require very high accelerations for retraction in order to maintain the printing speed. And this is where another disadvantage of the Bowden setup comes into play, the high level of friction. The extruder needs a lot of force to be able to push the filament through the Bowden tube, which limits the acceleration of the extruder for retraction. The Pi tower reveals these limitations. But what about the details? Well, yes, there are fallen lines, which is pretty normal since for numbers like D4 or D9 multiple parts are printed in the air. Other than that, there are no signs of stringing or under extrusion. The first layer was on point, there are no signs of squish or under extrusion, and the top layers are, there are also quite good. No signs of over extrusion at all, so for a Bowden setup, I think this is more than fine. For comparison, here are a couple of prints of the tower I found on printables. As you can see in the samples, many printers have a hard time printing this torture test. In the past, I have shown that the cooling system of the printer is able to print an overhang of 80 degrees at a speed of 160 mm per second without any slowdown. However, this test was done in optimal conditions since the fan duct was blowing directly on the front of the overhang test. So I wanted to repeat this test and see if there were any weak points in the cooling system. I found this nice overhang test that also combines a bridging test. I liked it a lot, but also it had a big problem. The overhangs end at an angle of 70 degrees. So I decided to double the speed so that we could see any signs of failure on the final print. Let's have a look at the printed part. Up to 60 degrees, the overhangs printed fine. At about 65 degrees, the first artifacts shown up. There was no difference in quality in comparison of all four sides of the print, which is exactly the outcome I was looking for. Also, 60 degrees is a good achievement considered the printing speed of 320 mm per second. Several people in the comments have asked me to get other YouTubers like Aurora Tech to review my printer. While I don't have any control over the content of others, I could borrow prints from them and do them here for comparison. This Robo Alpaca was printed at the size of 75% in approximately 90 minutes. It was necessary to reduce the size to fit it into the printing area. It was printed at a maximum speed of 600 mm per second for the infills and a speed of 320 mm per second for the outer perimeters. So let's have a look at the quality. There are no visible layer lines or signs of vibration on the outer surface. I mean, look at the details. I don't know if you can tell it from the video footage, but by eye, I would say this is a perfectly fine print. But have a look for yourself. I've uploaded high resolution images of all my prints today to Instagram. Another question that has been asked a few times is, what are the limits of 3D printing? Well, I can't say for sure. At the moment, I'm limited by the flow of my hot end, but that will change in the future. I am currently developing my own hot end. The first prototype is ready, and without giving too much away, it will be the fastest hot end in the world. If you don't want to miss that release of this hot end, please subscribe. For sure, I will record a video on it with a couple of very fast prints. The last print that I have prepared for you is a Gridfinity print. If you have been subscribed to my channel for a while, you probably already know this short about a Gridfinity print at 650 mm per second. Well, what would happen if we double the speed and quadruple the acceleration? Well, you'll have to see it for yourself. This print was completed in 5 minutes and 45 seconds. As far as I know, this is the fastest Gridfinity print I've seen so far. If you want to see how fast you could do it, I've linked the STL file into the video description. And don't forget to share your print time with me and the community. I'm curious how fast you were able to print it. For comparison, this print took 98 minutes to print on a standard NF3 printer. So let's have a look at the quality. Well, first of all, at these speeds the quality can't be perfect, and it doesn't have to be. A Gridfinity box is a functional part that has to be positional accurate to fit into the grid. So the first thing I see is that there is no under extrusion on either the top or the bottom layer, which is a good indicator because we printed at about 75 cubic millimeters. There are some acceleration artifacts on the outer surface, not much, but they are visible. You can also see under extrusions on the seam line where the layer started. Here, pressure advanced was a little too aggressive and caused this problem. I've done my best to optimize this, but it seems that at these speeds you can't use linear pressure compensation anymore. But overall the box looks good. The first layer was on point, even without autobat leveling. Let's see how the overhangs looks like. Well, I can't see any fallen lines, and I can't feel any fallen lines, so even at those speeds the cooling system was on point. Honestly, I like the way how this thing turned out. So this was it for today. Thanks for watching. Feel free to give me feedback on what you like me to print in a future video. Also, if you want to build a D100 by yourself, take a look at the video description. I've added all the resources you need to get started. And now, get out of here.